At the top, you have your essential questions. When we talk about organic chemistry, we're really focusing in on carbon because carbon is found in all the molecules of living things. So we're going to be looking at how these molecules are built, examples, and the functions of these molecules, why living things need these molecules. So we focus first on the atom or the element carbon. It has 4 valence electrons, which means that it's 4 electrons short of having a full octet, which means that it's likely to form 4 bonds. It's not very electronegative, so most of these bonds are going to be nonpolar covalent. But we do want to kind of keep in mind that's just most of the bonds being nonpolar. Carbon could bond to oxygen, which could then kind of change the polarity of the bond. But for the most part, carbon is going to be sharing the electrons very equally. One very common element that we see are what are called hydrocarbons. The name literally explains it, carbons and hydrogens. And so they are made just of carbon and hydrogen, no oxygen yet, so just carbon and hydrogen. And they are going to be very, very nonpolar. The electrons are going to be shared very equally. We've got kind of different levels of building, so one thing that we'll see are basically chains. So hydrocarbons are often seen in chains. And as we add each carbon, it's going to become what we call saturated with hydrogens. So we are saturated with these hydrogens, meaning that every available carbon bond is filled with a hydrogen. And so these are actually going to be a lot of our fuels. Propane, methane, ethane, butane, all of these are examples of hydrocarbons. There's energy, remember, in a bond. That electron being shared is holding some potential energy. One of the big things that we want to pay attention to here, for example, is we've got butane and isobutane. So it's named butane because it has 4 carbons, but we see a slightly different shape here. And we know that the shape is going to be important. So the shape of the molecule is going to determine its function. So shape determines function. FXN is how I abbreviate it. And isomers are just names for different shapes. So isomers tell us that we have different shapes, but the same chemical formula. So butane and isobutane are both going to be C4H10, but they're just shaped slightly differently. We will also start to see rings. So you just need to be able to recognize that we can have isomers or different shapes of a hydrocarbon, and that they will sometimes fold into a ring shape. In terms of naming, you don't really need to memorize the names. That's a little bit more organic chemistry. But if you'll just notice A and E is going to be the suffix of all of these. When we get into double bonds, sometimes we'll talk about ene. Triple bonds would give us ines, Y-N-E, but you really don't need to know that for your basic AP Bio class. What we do need to know is that we can actually add things on to the carbon skeleton. So these pictures up here would be carbon skeletons. We can add things onto it. For example, an OH group, which you've already seen when we looked at morphine. We saw these OH groups. Well, we know that the addition of a oxygen and a hydrogen is going to make it more polar. So a lot of times adding these, what are called functional groups, is going to therefore change the behavior of the molecule. So here we've got estradiol, which is basically estrogen, and testosterone. They have the same basic carbon skeleton, but different functional groups, different groups on the end. This is a double bonded O. We know that these are different in polarities. Double bond is going to signify some more non-polar properties, but this O and H is going to make it more polar. So these are the two sex hormones, and this is what gives us a lot of the differences in the sex features, the gender features. And we're talking about very small differences in the molecule having a big effect in the function. So the behavior of that molecule, is it polar? Is it nonpolar? Does it dissolve in water? So we have a couple functional groups that we need to learn. And the main thing is we need to learn the name as well as the properties of it. So this first one is called hydroxyl. And as you can see, we're going to have increased polarity. The next one is called a carbonyl. This is when we have a O double bonded to a C. We're going to have kind of medium polarity, not very high, but definitely more than if the oxygen weren't there at all. This one is called carboxyl. It's kind of a combination of the carbonyl and the hydroxyl. Bonded to the carbon is the double O, but also the OH. If this double O is on the exterior of the molecule, it's actually called an aldehyde. If it's buried deeper in on another carbon, then it's called a ketone. And that applies for the carbonyl as well. So if it's on the end or if it's in the middle, we've got aldehyde on the outside and ketone on the inside. This is an amine group. If you remember ammonia from chemistry, this is a sulfahydryl group. And here we just have a phosphate. Big thing to notice about the phosphate group is we do actually have a charge, not just polarity, but a charge. And so the charge is going to make it very attracted to that water molecule, so very water soluble. It will dissolve very easily in water. So the big things to pay attention to here are kind of the endings. You might see these at the ends of words, and they'd be able to expect you to identify that it would have these functional groups. And we kind of want to notice that we're starting to go towards chenops: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So we will see these groups in our living molecules, in the organic molecules that we see in living things. So just taking some time to kind of get these memorized and focusing on what they do to the polarity. Here we're going to have slightly higher polarity, but the hydroxyl is kind of going to be one of the highest. The phosphate is going to be kind of the highest in terms of attraction to water because of that charge. The amine and the sulfahydryl are kind of medium as well. They still change the behavior of a hydrocarbon, but the ones with oxygen have a larger effect and the phosphate has the largest. So you want to take a second and think about why carbon allows for diverse molecules. Think about the number of bonds that a carbon can form. And then we want to go on and talk about carbohydrates. But you do want to go back and know what a hydrocarbon is. You want to be able to look at a molecule and identify some groups that are present there. And we're going to talk much more about this molecule itself later. See if you can figure out the name based on the functional groups. So the other part of the notes that we need to talk about is how do we synthesize? If we're talking about eventually building a living thing, a cell, how do we build a cell? Well, we need to build the cell membrane. Well, that's made of a phospholipid. How do we build a lipid? And so we're going to start by talking about these words monomer and subunit. They mean the same thing. They basically mean the building block. They can exist individually, such as glucose, which is just a single building block by itself, or they can be made into polymers or repeating units. So knowing the relationship between these four words, monomer and subunit means small part, polymer and macromolecule mean larger molecules built of these small parts. So we'll be looking at each of the small parts a little bit later. But we're going to focus mainly on how to build them. Synthesis, dehydration synthesis would mean to remove water. So if I have these two monomers or small parts and I add them together, I'm actually going to remove the OH and this H, and I'll end up with an O left as bonding them together in the middle. And so water was actually removed. So anytime I'm joining two subunits, I'm always removing water, and that creates an environment where the two want to bond together. And that is called dehydration synthesis. This is usually going to require enzymes, which we'll talk more about later in this unit. We can actually do the opposite. If we remove water to build, we can actually add water and an enzyme to break. And that's what hydrolysis means. Breaking and using water to break that bond. So we need to know dehydration synthesis, what it means, what it's doing, and then we need to know what hydrolysis means and what it is doing.
Oops, sorry.
It's